Non-metallic sheath cable, often referred to as an M cable, is a common type of electrical wiring used in residential buildings. Its installation is governed by the National Electrical Code, or NEC, which sets standards for safe electrical practices. Section 334.15 of the NEC addresses the securing and supporting of NM cable. This section mandates that NM cable must be secured to the building structure in such a way that it closely follows the surface of the building finish or running boards. The intention is to provide physical protection to the cable and prevent it from being subjected to strain or damage. When cavities are filled with urethane foam insulation, the question arises whether stapling NM cable to the bottom of joists within those cavities meets the requirement of closely following the surface of the building finish. Urethane foam insulation, when foamed in place, expands to fill the available space, creating a thermal barrier and an air seal. However, it is critical to consider the properties of the foam and its interaction with the cable. Firstly, the nature of the insulation material is important. Urethane foam is typically rigid or semi-rigid when cured. While it provides support to the cable, it does not constitute a building finish in the traditional sense, such as drywall or wood sheathing. The NEC intent is for the cable to be affixed to a solid surface that provides ongoing support and protection. Secondly, the method of attachment is a key consideration. Stapling the NM cable to the joist and then encasing it in foam does secure it in place initially. However, the foam itself may not provide sufficient long-term support to prevent sagging or movement of the cable, especially under its own weight or due to temperature changes. The expansion and contraction of the foam over time could also exert stress on the cable. Thirdly, the code requirement to closely follow the surface is not met simply by the cable being surrounded by foam. The surface referred to in the code typically implies a continuous, solid surface like the face of a stud, joist, or a running board. The foam, while filling the cavity, does not provide that continuous surface for the cable to adhere to in a manner that ensures it is closely following it. Consider alternatives to stapling NM cable directly to the bottom of joists in foam-filled cavities. One approach is to install running boards with furring strips along the joists before the foam is applied. The NM cable can then be secured to these running boards, ensuring it closely follows a solid surface. Another option is to use cable ties or straps to support the cable from the joists in a manner that prevents it from coming into direct contact with the foam, while still providing adequate support. When installing NM cable in insulated cavities, it is essential to consider the potential for heat buildup. NM cable is rated for a specific temperature, and exceeding that temperature can degrade the insulation and pose a fire hazard. While foam insulation provides thermal resistance, it can also trap heat generated by the cable itself, especially if the cable is carrying a significant load. It's important to ensure that the cable is properly sized for the load it will carry and that the insulation does not create an environment that could lead to overheating. The NEC provides guidelines for directing cable ampacity in high-temperature environments. These guidelines should be consulted when installing NM cable in insulated cavities. Another aspect to consider is the potential for the foam insulation to react with the cable jacket. Some types of foam insulation may contain chemicals that can degrade the plastic insulation of the NM cable over time. It is important to verify that the foam insulation is compatible with the cable jacket material. Consult the foam insulation manufacturer's specifications to ensure compatibility. It is also crucial to maintain proper spacing between the NM cable and other objects within the insulated cavity. Avoid running the cable in direct contact with metal objects or other potential sources of abrasion. This can prevent damage to the cable jacket and reduce the risk of electrical shorts. Ensure that all electrical connections within the cavity are properly made and protected. Use approved connectors and enclosures to prevent moisture or contaminants from entering the connections. Loose connections can generate heat and pose a fire hazard. Regularly inspect NM cable installations in insulated cavities to identify any signs of damage such as cracks, abrasions, or discoloration of the cable jacket. Address any issues promptly to prevent potential electrical problems. Consider future accessibility when installing NM cable in insulated cavities. If the cable needs to be accessed for repairs or modifications in the future, it may be necessary to remove some of the foam insulation. Plan the installation in a way that allows for relatively easy access to the cable without compromising the integrity of the insulation. When penetrating the foam insulation with NM cable, seal the penetration points to prevent air leakage and moisture ingress. Use approved sealant or caulk to create a tight seal around the cable. This will help maintain the thermal performance of the insulation and prevent condensation from forming within the cavity. Ensure that all electrical work is performed by qualified and licensed electricians who are familiar with the NEC and local building codes. Proper installation techniques and adherence to code requirements are essential for ensuring electrical safety. Always consult with a qualified electrical inspector to ensure that the NM cable installation meets all applicable codes and regulations. Electrical inspections can help identify potential hazards and ensure that the installation is safe and compliant. In conclusion, simply stapling NM cable to the bottom of joists and encasing it in urethane foam insulation does not typically meet the NEC requirement of closely following the surface of the building finish. Alternative methods of securing and supporting the cable should be used to ensure compliance and electrical safety. It's very important to properly size the wires that will be used. Wire sizing involves selecting the appropriate gauge of electrical wire for a specific application, ensuring it can safely carry the intended electrical current without overheating or causing voltage drop. This process is crucial for electrical safety and code compliance. Firstly, you need to determine the load requirements. Calculate the total amperage that the circuit will need to carry. This involves summing up the amperage of all the devices and appliances that will be connected to the circuit. Refer to the appliance nameplates or manufacturer's specifications to find the amperage ratings. Secondly, calculate the continuous load. If the circuit will supply power to loads that operate continuously for 3 hours or more, such as lighting or heating systems, the NEC requires that the circuit be sized to handle 125% of the continuous load. This is to prevent overheating of the wiring. Thirdly, consult the ampacity tables. The NEC provides ampacity tables that list the maximum allowable current carrying capacity of different wire sizes based on their insulation type and installation conditions. Refer to Table 310.15b16 in the NEC for ampacity ratings. Fourthly, make corrections and adjustments. The ampacity ratings in the NEC tables are based on specific conditions such as ambient temperature and the number of current-carrying conductors in a raceway or cable. If the actual conditions differ from those specified in the tables, you may need to apply correction and adjustment factors to the ampacity ratings. Fifthly, account for voltage drop. Voltage drop is the reduction in voltage that occurs along the conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction and reduce its efficiency. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. Use voltage drop calculators or consult engineering tables to determine the appropriate wire size to minimize voltage drop. Sixthly, select the appropriate wire size. Based on the calculated amperage, ampacity ratings, and voltage drop considerations, select the smallest wire size that can safely carry the intended current without exceeding its ampacity rating or causing excessive voltage drop. Seventhly, consider the insulation type. The type of insulation used in the wire affects its ampacity rating and suitability for different applications. Common insulation types include THHN, THWN, and XHHW. Choose an insulation type that is appropriate for the environment in which the wire will be installed. Eighthly, verify overcurrent protection. Ensure that the circuit is protected by an overcurrent protection device such as a circuit breaker or fuse that is properly sized to protect the wiring. The overcurrent protection device should have an ampacity rating that is no greater than the ampacity of the wire. Ninthly, follow local codes and regulations. Local electrical codes and regulations may have additional requirements for wire sizing. Consult with local authorities or a qualified electrician to ensure compliance with all applicable codes. Tenthly, document your calculations. Keep a record of all wire sizing calculations and the factors considered. This documentation can be helpful for future reference and for demonstrating compliance with code requirements. Correctly sizing electrical wires is essential for safety and performance. Undersized wires can overheat and cause fires, while oversized wires can be unnecessarily expensive. By following the steps outlined above and consulting with qualified professionals, you can ensure that your electrical wiring is properly sized for its intended application. Also ensure you are using the correct staple when securing the wires. When securing electrical wires with staples, it is important to use the correct type and size of staple to avoid damaging the wires and creating a safety hazard. Firstly, use insulated staples. Insulated staples are designed with a plastic or rubber coating that prevents the metal staple from coming into direct contact with the wire insulation. This helps to protect the wire insulation from damage and reduces the risk of electrical shorts. Secondly, select the appropriate staple size. The size of the staple should be appropriate for the size of the wire being secured. Use a staple that is large enough to securely hold the wire in place, but not so large that it could damage the wire insulation. Thirdly, avoid over-tightening the staples. Over-tightening the staples can compress the wire insulation and damage the wires. Use just enough pressure to securely hold the wires in place without crushing them. Fourthly, use the correct staple gun or hammer. Use a staple gun or hammer that is designed for installing insulated staples. This will help to ensure that the staples are installed properly and without damaging the wires. Fifthly, inspect the staples after installation. After installing the staples, inspect them to ensure that they're properly seated and that they are not damaging the wires. If any staples are loose or damaged, remove them and replace them with new staples. Sixthly, follow the NEC guidelines. The NEC provides guidelines for securing electrical wires with staples. Consult the NEC for specific requirements regarding staple type, size, and spacing. Seventhly, consider the wire type. Type of wire being secured may affect the type of staple that should be used. For example, an M cable requires a different type of staple than armored cable. Eighthly, avoid using metal staples on an M cable. Metal staples should not be used on an M cable because they can damage the cable insulation and create a fire hazard. Use only insulated staples that are specifically designed for use with an M cable. Ninthly, use cable ties as an alternative. Cable ties can be used as an alternative to staples for securing electrical wires. Cable ties are less likely to damage the wires and can be easier to install in some situations. Tenthly, consult with a qualified electrician. If you are unsure about the correct type or size of staple to use, consult with a qualified electrician. An electrician can provide guidance and ensure that the wires are secured properly. Also consult the NEC for box fill calculations. Box fill calculations are essential for ensuring the safe and proper installation of the electrical wiring in junction boxes, outlet boxes, and switch boxes. These calculations determine the maximum number of wires, devices, and fittings that can be safely contained within a box without overcrowding, which can lead to overheating, insulation damage, and potential fire hazards. Firstly, determine the box size. Measure the internal dimensions of the electrical box, including its height, width, and depth. These dimensions are typically stamped on the inside of the box or can be found in the manufacturer's specifications. Secondly, calculate the box volume. Calculate the internal volume of the box in cubic inches. For rectangular boxes, the volume is calculated by multiplying the height, width, and depth. For other box shapes, such as round or octagonal boxes, consult the NEC for the appropriate volume calculation method. Thirdly, determine the conductor fill allowance. The NEC specifies the number of conductors of different sizes that are allowed in a box based on its volume. Refer to Table 314.16 in the NEC for conductor fill allowances. The conductor fill allowance is expressed in terms of the number of conductors of a given size that can be accommodated in the box. Fourthly, count the number of conductors. Count the total number of conductors that will be entering the box, including all hot wires, neutral wires, and ground wires. Each conductor that terminates or passes through the box must be counted. Fifthly, apply adjustment factors. The NEC requires adjustment factors to be applied to the conductor current in certain situations. For example, if the box contains equipment grounding conductors or conductors that are spliced together, adjustment factors must be applied to account for the additional space occupied by these conductors. Sixthly, calculate the total conductor fill. Calculate the total conductor fill by multiplying the number of conductors of each size by their corresponding conductor fill allowance from Table 314.16 in the NEC. Sum up the results for all conductor sizes to obtain the total conductor fill. Seventhly, determine the device fill allowance. If the box contains devices such as switches, receptacles, or dimmers, a device fill allowance must be added to the total conductor fill. The device fill allowance is specified in Table 314.16b in the NEC and is based on the size and type of device. Eighthly, determine the equipment grounding conductor fill allowance. If the box contains equipment grounding conductors, an equipment grounding conductor fill allowance must be added to the total conductor fill. The equipment grounding conductor fill allowance is specified in Table 314.16b5 in the NEC. Ninthly, determine the clamp fill allowance. If the box contains internal cable clamps, a clamp fill allowance must be added to the total conductor fill. The clamp fill allowance is specified in Table 314.16b4 in the NEC. Tenthly, calculate the total box fill. Calculate the total box fill by summing up the total conductor fill, the device fill allowance, the equipment grounding conductor fill allowance, and the clamp fill allowance. 11thly, compare the total box fill to the box volume. Compare the total box fill to the internal volume of the box. The total box fill must not exceed the box volume. If the total box fill exceeds the box volume, a larger box must be used. 12thly, follow local codes and regulations. Local electrical codes and regulations may have additional requirements for box fill calculations. Consult with local authorities or a qualified electrician to ensure compliance with all applicable codes. 13thly, document your calculations. Keep a record of all box fill calculations and the factors considered. This documentation can be helpful for future reference and for demonstrating compliance with code requirements. Performing box fill calculations is essential for ensuring the safe and proper installation of electrical wiring. Overcrowded boxes can lead to overheating, insulation damage, and potential fire hazards. By following the steps outlined above and consulting with qualified professionals, you can ensure that your electrical boxes are properly sized and filled. Remember to also understand the requirements for using conduit. Using electrical conduit involves installing a protective tubing system to enclose and protect electrical wiring. Conduit provides mechanical protection for the wiring, prevents it from being damaged by moisture, chemicals, or physical abrasion, and helps to contain potential electrical hazards. Firstly, determine the type of conduit needed. Select the appropriate type of conduit for the application, based on factors such as location, environment, and code requirements. Common types of conduit include rigid metal conduit, or RMC, intermediate metal conduit, or IMC, electrical metallic tubing, or IMT, flexible metal conduit, or FMC, liquid-type flexible metal conduit, or LFMC, and rigid polyvinyl chloride conduit, or PVC. Secondly, plan the conduit route. Plan the route that the conduit will follow, taking into account factors such as accessibility, obstructions, and code requirements. The conduit route should be as direct as possible and should avoid sharp bends or unnecessary turns. Thirdly, measure and cut the conduit. Measure the length of conduit needed for each section of the route and cut the conduit to size using a pipe cutter or saw. Ensure that the cut ends are smooth and free of burrs. Fourthly, deburr the conduit end. Use a deburring tool to remove any burrs or sharp edges from the cut ends of the conduit. This will prevent damage to the wiring insulation when it is pulled through the conduit. Fifthly, install conduit fittings. Install the appropriate fittings on the ends of the conduit sections, such as couplings, connectors, elbows, and tees. Use a wrench or pliers to tighten the fittings securely. Sixthly, support the conduit. Support the conduit at regular intervals using conduit clamps, straps, or hires. The spacing between supports should comply with the NEC and local code requirements. Seventhly, pull the wiring through the conduit. Use of fish tape or wire pulling lubricant to pull the electrical wiring through the conduit. Be careful not to damage the wiring insulation during the pulling process. Eighthly, connect the conduit to electrical boxes and enclosures. Connect the conduit to electrical boxes, enclosures, and equipment using appropriate connectors. Ensure that the connections are tight and secure. Ninthly, ground the conduit system. Ground the metal conduit system in accordance with the NEC and local code requirements. This typically involves connecting the conduit to a grounding electrode conductor or a grounding busbar. Tenthly, inspect the installation. Inspect the completed conduit installation to ensure that it is properly installed, supported, and grounded. Check for any loose connections, damaged conduit, or other potential hazards. 11thly, follow local codes and regulations. Local electrical codes and regulations may have additional requirements for conduit installation. Consult with local authorities or a qualified electrician to ensure compliance with all applicable codes. 12thly, document your installation. Keep a record of all conduit installation details, including the type of conduit used, the size of the conduit, the route of the conduit, and the grounding method. This documentation can be helpful for future reference and for demonstrating compliance with code requirements. Using electrical conduit is an important part of ensuring the safety and reliability of electrical wiring systems. By following the steps outlined above and consulting with qualified professionals, you can ensure that your conduit installation is properly designed, installed, and maintained. Also consider using GFCI protection. Ground fault circuit interrupter, or GFCI, protection is a critical safety measure designed to protect people from electrical shock. A GFCI is a device that monitors the electrical current flowing in a circuit and quickly shuts off the power if it detects a ground fault, which is a dangerous condition where current leaks to ground. Firstly, understand the purpose of GFCI protection. The primary purpose of GFCI protection is to prevent electrical shock injuries and fatalities. GFCIs are designed to detect even small amounts of current leakage to ground and to interrupt the circuit before the current can cause serious harm. Secondly, identify locations requiring GFCI protection. The NEC requires GFCI protection in certain locations where there is a higher risk of electrical shock, such as bathrooms, kitchens, garages, outdoor areas, and near swimming pools. Refer to the NEC for specific requirements regarding GFCI protection in different locations. Thirdly, select the appropriate type of GFCI. There are two main types of GFCIs: receptacle type GFCIs and circuit breaker type GFCIs. Receptacle type GFCIs are installed in place of standard electrical receptacles, while circuit breaker type GFCIs are installed in the electrical panel. Choose the appropriate type of GFCI for the application based on factors such as location, wiring configuration, and code requirements. Fourthly, install the GFCI correctly. Install the GFCI in accordance with the manufacturer's instructions and the NEC. Ensure that the wiring connections are tight and secure. Fifthly, test the GFCI regularly. Test the GFCI regularly to ensure that it is functioning properly. Press the test button on the GFCI to simulate a ground fault. The GFCI should trip and shut off the power to the circuit. If the GFCI does not trip, it may be defective and should be replaced. Sixthly, understand the limitations of GFCIs. GFCIs are designed to protect against electrical shock hazards, but they do not protect against overloads or short circuits. Overcurrent protection devices, such as circuit breakers and fuses, are needed to protect against these types of electrical faults. Seventhly, avoid tampering with GFCIs. Do not tamper with GFCIs or attempt to bypass their safety features. GFCIs are designed to protect lives, and tampering with them can create a serious safety hazard. Eighthly, replace defective GFCIs promptly. If a GFCI fails to operate properly or is damaged, replace it promptly. Defective GFCIs can leave you vulnerable to electrical shock hazards. Ninthly, educate others about GFCI protection. Educate family members, coworkers, and others about the importance of GFCI protection and how to test and maintain GFCIs. Tenthly, follow local codes and regulations. Local electrical codes and regulations may have additional requirements for GFCI protection. Consult with local authorities or a qualified electrician to ensure compliance with all applicable codes. GFCI protection is an essential safety measure that can help prevent electrical shock injuries and fatalities. By following the steps outlined above and consulting with qualified professionals, you can ensure that your electrical system is properly protected by GFCIs. In addition to NM cable, consider the use of other wiring methods. Several wiring methods are available for electrical installations, each with its own advantages and disadvantages. Understanding these different methods and their appropriate applications is crucial for ensuring a safe and compliant electrical system. Firstly, consider armored cable. Armored cable, also known as AC cable or BX cable, consists of insulated conductors wrapped in a flexible metal sheath. AC cable provides excellent mechanical protection for the conductors and is often used in exposed locations or where the wiring may be subject to physical damage. Secondly, understand electrical metallic tubing. Electrical metallic tubing, or IMT, is a thin-walled metal conduit that is commonly used for indoor wiring in commercial and industrial buildings. EMT provides good protection for the conductors and is relatively easy to install. Thirdly, learn about rigid metal conduit. Rigid metal conduit, or RMC, is a thick-walled metal conduit that provides the highest level of mechanical protection for electrical wiring. RMC is typically used in harsh environments or where the wiring may be subject to severe physical damage. Fourthly, be aware of flexible metal conduit. Flexible metal conduit, or FMC, is a flexible metal conduit that is used for short runs or where flexibility is needed. FMC is often used to connect equipment to junction boxes or to provide flexibility in tight spaces. Fifthly, know about liquid-tight flexible metal conduit. Liquid-tight flexible metal conduit, or LFMC, is a flexible metal conduit that is covered with a liquid-tight plastic coating. LFMC is used in wet or damp locations or where the wiring may be exposed to chemicals or other corrosive substances. Sixthly, explore rigid polyvinyl chloride conduit. Rigid polyvinyl chloride conduit, or PVC, is a non-metallic conduit that is lightweight, corrosion-resistant, and easy to install. PVC conduit is often used underground or in corrosive environments. Seventhly, learn about electrical non-metallic tubing. Electrical non-metallic tubing, or ENT, is a flexible non-metallic conduit that is used for indoor wiring in residential and commercial buildings. ENT is lightweight, easy to install, and resistant to moisture and chemicals. Eighthly, know about surface raceway. Surface raceway is a type of wiring system that is installed on the surface of walls or ceilings. Surface raceway is often used in retrofit applications or where it is not practical to run wiring inside walls or ceilings. Ninthly, be aware of cable trays. Cable trays are open support systems that are used to support large numbers of cables in commercial and industrial buildings. Cable trays are typically used for power cables, control cables, and communication cables. Tenthly, consider wireways. Wireways are enclosed troughs or channels that are used to protect and support electrical wiring. Wireways are often used in industrial buildings or where the wiring needs to be protected from physical damage. 11thly, understand direct burial cable. Direct burial cable is a type of cable that is designed to be buried directly in the ground without the need for conduit. Direct burial cable is typically used for underground power distribution or for connecting outdoor equipment. 12thly, follow local codes and regulations. Local electrical codes and regulations may restrict the types of wiring methods that are allowed in certain applications. Consult with local authorities or a qualified electrician to ensure compliance with all applicable codes. Understanding the different wiring methods available and their appropriate applications is essential for designing and installing a safe and compliant electrical system. By considering the factors outlined above and consulting with qualified professionals, you can choose the wiring method that is best suited for your specific needs.